Okay, page 593, number 2. And for these ones, you're going to use the chart on page 592 for the mercury atom. Okay, so number 2 says a mercury atom drops from the 8.82 electron volt level, so that's E initial is 8.82 electron volts, to the 6.67 electron volts, so E final is 6.67 electron volts. So they have to tell you this. It didn't have to tell you the levels in hydrogen because we could find them. But for every other atom, they're going to have to tell you. So it wants to know what is the energy of the photon emitted. So remember, EP is equal to E final minus E initial. So EP is equal to 6.67 electron volts minus an 8.82 electron volts. And you end up getting an EP of negative 2.15 electron volts, where again the negative means emitted. That's part A. Part B says, what is the frequency of the photon? So we know EP is equal to HF, so F is equal to that EP divided by H. So you can drop the negative, it just meant emitted. 2.15 electron volts times 1.602 to the negative 19 joules per electron volt, because it has to be in joules before you divide it by Planck's constant, because Planck's constant units are joule seconds. And when you do this, you get a frequency of 5.198 times 10 to the 14th hertz. Okay, number 2. Number 3, and it tells you now to use the chart. So a mercury atom is in an excited state when its energy level is 6.67 electron volts. Okay, so 6.67 electron volts above the ground state. A photon of energy 5.12, so this is energy of the photon, 5.12 electron volts. But it's not, it's 2.15. 2.15, at least I had the right numbers. Strikes a mercury atom and it's absorbed. To what level is the mercury atom raised? So this is actually the initial. I just wasn't sure, so I didn't want to put anything in there. So we have the initial, we have the energy of the photon, we're looking for the final. So EP is equal to E final minus E initial. Rearranging then, E final, which is what we're looking for, is equal to EP plus E initial. So 2.15 electron volts plus 6.67 electron volts. I think I recognize this. 8.82 electron volts. It could be just the reverse of the one above. Okay, and then it wants to know to what energy level did the mercury atom raise. So now you go to the chart. I just happen to have a photocopy of that chart. So you go to the chart, and if you can see it, you find which one it is. 1, 2, 3, 4, 5, 6, 7, 8. It's the 9. And so it's N equals 9 is the level to which it was raised. Number 4 says a mercury atom is in an excited state at the E6 level. And so if you look, E6, now I didn't talk about this, but you can use either the positive side or the negative side. Okay? In hydrogen, we only have the negatives, but these are the same. You'll notice the positive side starts with the ground state being 0 and goes up to ionization, which is 10.38. The negative side, the ground state is negative 10.38, and it goes up to the ionization, which is 0. So for fun, let's use the negative side, since the first two use the positive. So if you look at the negative side and find your E6, it's negative 2.68 electron volts. And then I lost the question. It wants to know how much energy would be needed to ionize it. And so ionizing is 0. And so EP is equal to EF minus EI. So EP is equal to 0 minus a minus 2.68 electron volts. And so EP is going to be equal to 2.68 electron volts. I like the negative side just because it's easier to figure out the ionization. You don't actually have to do any math, it's just going to be that one. Okay, if you did use the other side, you would get exactly the same answer. Okay, so that's for A. For B, how much energy would be released if the electron dropped from the E2 down to the E2 level instead? So if it's now it's going to go from E6 to E2. Okay, so E of the photon will be E2 minus E6. Looking at our chart, E2 is negative 5.74. So negative 5.74 electron volts minus a negative 2.68 electron volts, and you get the energy of the photon to be negative 3.06 electron volts, and of course the negative means the photon's being emitted. That is number 4. Number 5 says a mercury atom is in an excited state that has an energy of negative 4.95 electron volts. So that's one of the E's. Okay? It absorbs a photon and is raised to the next energy level. What is the energy of the photon? So you need to look at the chart and find the 4.95 and then find the next level. This one's E4, by the way. And when you look, E5 is negative 3.71. And so now you're looking for the energy of the photon, final minus initial, so 5 minus 4. So negative 3.71 electron volts minus a minus 4.95 electron volts. You get an energy of a photon to be 1.24 electron volts. It works out to be positive, which means it's absorbed, right? Because it's hopped up. That's 5A. 5B, what is the photon's frequency? So again, EP is equal to HF. So F is equal to EP over H. So 1.24 electron volts times the conversion factor to go into joules divided by Planck's constant, 6 times 10 to the negative 34 joule seconds, and you should get a frequency here of 2.998 times 10 to the 14th hertz. Okay, so that's 1 to 5 on that page, but then I asked you to do number 4 and 5 on the applying concepts. So number 4 says a photon with an energy of 6.2 electron volts enters a mercury atom in the ground state. Will it be absorbed by the atom? I think I have to switch to a better chart. Here's the colored one. Okay, so it's going to absorb 6.2 electron volts. Okay, and it's in the ground state. So the ground state here, if I look at this side, the ground state is 0, and if it takes in 6.2, look, there is no energy level that's at 6.2. So remember, it has to exactly match, and it's not going to do that, right? It's too big to go to the 5.43. It's too small to go to the 6.67. So the question wants to know, will it be absorbed? No. Number 5 says, a certain atom has energy levels shown here. If an electron can make transitions between any two levels, how many spectral lines can the atom emit? And then which transition will give you the highest one? So if it can go from any, then it can go from 2 down to 1, that's 1, 3 down to 1, that's 2, 4 down to 1, that's 3. But it can also go from 3 down to 2, that's 4, 4 down to 2, that's 5, and 4 down to 3, that's 6. So there's 6 possible spectral lines that can be formed here. Which one will have the greatest energy? The one with the biggest drop, so from 2 to 1. Okay, and finally, that's all your homework questions.